In the previous presentation, we developed a mathematical model for the first law of thermodynamics. This model, called an energy balance, is used to determine the change of the total energy contained in a system during a process by accounting for all of the energy entering and leaving the system. The change in the total energy contained in the system, which is equal to the change in the sum of the internal energy, the kinetic energy, and the potential energy of the system, is equal to the sum of all of the energy transferred by heat into and out of the system, plus the sum of all of the energy transferred by work into and out of the system, plus the sum of all of the energy transferred into the system by mass flow, minus the sum of all of the energy transferred out of the system by mass flow. Note that in this energy balance, heat transferred into the system is positive because it increases the total energy of the system, while heat transferred out of the system is negative because it decreases the total energy of the system. Similarly, work done on the system is positive, while work done by the system is negative. It's useful to write our energy balance in a rate form, especially when mass is flowing into and/or out of our system. The change in total energy of the system with time, or the rate of change of energy of the system, is equal to the sum of the rate at which heat energy is transferred into and out of the system, plus the sum of the rate at which work energy is transferred into and out of the system, plus the rate at which energy is transferred into the system by mass flow, minus the rate at which energy is transferred out of the system by mass flow. You may have noticed that there are different symbols used for the time derivatives. Some of these derivatives use the letter d to represent a differential amount. These are called exact differentials. Differential amounts of heat and work are denoted by the delta symbol. These are called inexact differentials. Let's take a look at these two types of differentials by comparing the rate of energy change to the rate of heat transfer. Let's integrate the rate of energy change over some process beginning at time 1 and ending at time 2. The delta t's cancel out, and our integral reduces to E2 minus E1, or delta E. This type of function is called a point function. The magnitude of point functions depend only on the state of the system, and not on how the system reaches that state. E1 and E2 are properties of the system at state 1 and state 2 respectively. All properties are point functions. Now let's integrate the rate of heat transfer from time 1 to time 2. Again, the delta t's cancel out. However, in this case, the result is simply equal to the total heat transferred from time 1 to time 2. Note that it's not equal to Q2 minus Q1. This would make no sense because heat is not a property of the system. In other words, there is no heat contained in the system at state 1 or state 2. Heat is an energy interaction and is only recognized as a total amount of energy gained or lost during a process as it crosses the system boundary. This type of function is called a path function. The magnitude of a path function depends on the path followed during the process as well as on the end state. Heat and work are path functions. We can simplify the rate form of the energy balance by writing time derivatives as the variable with a dot over the top as follows. Note that by integrating this equation over time, we arrive back at our original expression for conservation of energy.